Hello friends, welcome to my lecture on Cauchy type integral equations. We will have a series of lectures on this topic. So this is first of those lectures. Let us first define a Cauchy principal value for integrals. Suppose we have a function fs which is defined in the interval a less than or equal to x less than or equal to b, and it is unbounded in the neighborhood of a point c which lies in between a and b. And if we assume that this function f is integrable in each of the intervals a to c minus epsilon and c plus eta to b, where eta, epsilon and eta are arbitrarily small positive real numbers, then the limit integral a to b fs ds, which is equal to limit epsilon tends to 0 eta tends to 0 integral over a to c minus epsilon fs ds plus integral over c plus eta to b fs ds, if it exists, is called the improper integral of the function fs in the range ab. Now here epsilon and eta tend to 0 independent of each other. Now it may happen that the limit here may not exist. So if the limit does not exist when epsilon and eta tend to 0 independently of each other, and exists if epsilon and eta are related, for example integral a to c minus epsilon, suppose we take the function fs equal to 1 over s minus c, where the real number c lies between a and b, then the function fs equal to 1 over s minus c will become unbounded in a neighborhood of c. So if you want to integrate the function 1 over s minus c over the interval a to b, then we will write it as integral a to c minus epsilon ds over s minus c plus integral over c plus eta to b ds over s minus c, and when you integrate this, what you will get is ln b minus c over c minus a plus ln epsilon over eta. If epsilon and eta tend to 0 independently of each other, then this value ln epsilon over eta will also vary. So if you consider epsilon and eta to be related, then the preceding limit exists. For example, we consider in the special case epsilon equal to eta, then when you take epsilon equal to eta here, then ln 1 is equal to 0. So integral a to c minus epsilon ds over s minus c plus integral c plus eta to b ds over s minus c will be ln b minus c over c minus a as epsilon goes to 0. So integral a to b ds over s minus c will be ln b minus c over c minus a. This value of the integral is called as the Cauchy principal value, or we call it as a Cauchy principal integral. Similarly, the Cauchy principal value of a function fs which becomes infinite at an interior point x equal to c of the range of integration ab is the limit. So in general, we can define the Cauchy integral principal value of a function fs as limit epsilon tends to 0 integral a to c minus epsilon plus integral c plus epsilon to b fs ds. That means we take eta to be equal to epsilon. Then when this limit exists, it is called as the Cauchy principal value of the function of the integral a to b fs ds. Now here epsilon is greater than 0 but less than or equal to minimum of c minus a b minus c, because we are considering a neighborhood of the point c. So epsilon has to be like that. Now such a limit, the notation for such a limit is p integral a to b fs ds. This p denotes the Cauchy principal value of the integral. We also write it as integral a to star b fs ds. So this star denotes the function fs is unbounded at some point in the open interval ab, and we are considering the Cauchy principal value of the integral. Similarly, if you have the consider the improper integral where the limits of integration are infinite, then the Cauchy principal value is given for the integral with an infinite range of integration like this: integral minus infinity to infinity fs ds equal to limit a tends to infinity b tends to infinity minus a to b fs ds. So this integral is defined like this. Now this limit may not exist when a and b tend to infinity independently of each other, but the limit exists when a is equal to b, then we call it as the principal value, Cauchy principal value. So limit a tends to infinity minus a to a fs ds is called the Cauchy principal value of the integral over minus infinity to infinity fs ds. Now the limits 3 and 4 are also called as singular integrals. So this is this is also called as singular integral. Similarly, the 3 is also called this one as the singular integral. Now such singular integrals exist when the function integrand fx satisfies the. So there is a condition which the function fs has to satisfy in order that these such singular integrals exist. So the condition is the called Holder condition. The function fx is said to satisfy the Holder condition if we can find constants k and alpha where 0 is less than alpha less than or equal to 1, such that whenever you take any 2 points x1 x2 in the range a less than or equal to x less than or equal to b, then mod of fx1 minus fx2 is less than k times mod of x1 minus x2 to the power alpha. If now in the particular case when alpha equal to 1, this condition is also known as the Lipschitz condition. A function which satisfies the Holder condition is called as Holder continuous, and when alpha is equal to 1, the condition is called the Lipschitz condition and the function is called as the Lipschitz continuous function. The Holder condition can also be extended to the case of functions of more than one variable. For example, if you take the kernel kxt in the integral equation, then the kernel kxt is Holder continuous with respect to both the variables x and t if we can find constants k and alpha, again 0 less than alpha less than or equal to 1, such that mod of k x1 t1 minus k x2 t2 is less than k times mod of x1 minus x2 to the power alpha plus mod of t1 minus t2 to the power alpha. Now where x1 t1 and x2 t2 are there in the range of integration of kxt. Now for the solution of Cauchy integral equations which we are going to discuss now a little later, for the solution of Cauchy type integral equations on a real line, let us study some identities which we shall use in order to find the solution of Cauchy type integral equations. So the first identity is minus integral 0 to u minus s over s to the power alpha ds upon u minus s into s minus t. The value of this integral is minus u minus t to the power alpha minus 1 over t to the power alpha pi cot alpha pi when 0 is less than t less than u, and here remember alpha is lying between 0 and 1. So 0 is less than alpha less than 1, and t minus u to the power alpha minus 1 t to the power alpha pi over sin alpha pi u less than t. So here the alpha is the condition on alpha is that 0 less than alpha less than 1. Now in order to prove this identity, consider the integral I equal to minus 0 to u minus 0 to u minus s divided by s raised to the power alpha ds upon u minus s into s minus t. Okay, now let us see how we transform this integral. So let us put u minus s equal to bs in this this equality. So let us put let u minus s equal to bs. When u minus s equal to bs, what we will get from here? R u minus s over s is equal to b. Also now this will imply that u upon s minus 1 equal to b. So this will imply that minus u by s square ds is equal to dv, and also the value of s we can find. So also u by s equal to b plus 1, u by s is equal to b plus 1, or we can say u upon b plus 1 is equal to s. So let us make this substitution in the above integral. We can see here that when when s is equal to 0, when s is equal to 0, v equal to infinity, and when s is equal to u, v equal to 0. So when s equal to 0, v becomes infinity, and when s is equal to 0, 1, when s is equal to u, s is equal to u, b is equal to 0. So I will be equal to minus integral infinity to 0 u minus s by s, u minus s by s is equal to b, so b to the power alpha, ds is equal to minus s square by u db, minus s square by u db, and then u minus s is equal to vs, and s minus t, u minus s is equal to bs, we can also write s minus t equal to u upon b plus 1, s is equal to u upon b plus 1 minus t. Okay, so what do we get? 0 to infinity. Now b to the power alpha upon b gives you b to the power alpha minus 1. Okay, and one s will cancel with one s here, so we will get s db by u into b, and we will put a negative sign here. So what we get is b to the power alpha minus 1, then we get s db divided by u, b we have already cancelled, so we have only u here, b we have already cancelled, so we have only u here, and then we get u minus b plus 1 into t by u. So this is equal to b plus 1 divided by u, and what we have here, we should get b to the power alpha minus 1 db s s upon u. Okay, yeah, b plus 1 is equal to u upon s. Okay, so yeah, so s upon u into b plus 1. Okay, s upon u into b plus 1 is equal to 1, so this is equal to minus integral 0 to infinity e b to the power alpha minus 1 divided by u minus b plus 1 into t db, or we can say that it is equal to integral 0 to infinity b to the power alpha minus 1 dv divided by bt minus u minus t. So this is what we get by making the substitution. We arrive at I equal to this is integral I, so I equal to integral 0 to infinity b to the power alpha minus 1 db upon bt minus u minus t. Now let us define xi to be like this. Then so define xi equal to bt upon u minus t in case 0 less than t less than u, and bt upon t minus u in the case u less than t. Okay, let us see. So this is I now. So let us see when we make this substitution what do we get. So then this I becomes okay. So let us say when we take 0 less than t, okay, let us take the case 1, 0 less than t less than u. Let us take this case. So in this case we are making the substitution xi equal to bt upon u minus t. So this gives you what b is equal to u minus t upon t into xi, and dv equal to u minus t upon t d xi. Further, now here what happens when b is equal to 0, xi is equal to 0, when v is equal to infinity, xi will be infinity because t is less than u. So b equal to infinity gives us since t is less than u. So the limits of integration will remain 0 infinity, and what we get b equal to u minus t by t. So u minus t divided by t raised to the power alpha minus 1, dv will be u minus t over t, d xi divided by bt is u minus t into xi, then minus u minus t. So this is equal to integral u minus t raised to the power alpha minus 1 divided by t raised to the power alpha minus 1 in t raised to the power alpha, and here u minus t d xi divided by u minus t into xi minus 1 we get. So 0 to infinity. So this will cancel and we will write it as 1 by t u minus t upon t raised to the power alpha minus 1 0 to infinity d xi upon xi minus 1. Similarly, and this I is nothing but this integral minus integral 0 to u minus s by s to the power alpha ds over u minus s into s minus t. Similarly, we can show when t is greater than u. In the case 2, similarly when u is less than t. Now when u is less than t, xi we are writing as t upon t minus u into b. So d xi equal to t upon t minus u dv. Further, when xi equal to 0, so we are writing the value of I now for the case when u is less than t. So xi is equal to 0 gives you b equal to 0 and xi equal to infinity. Now when u is less than t, t upon t minus u is a positive quantity, so xi equal to infinity gives you b equal to infinity. B equal to no, we have to write it like this. B equal to 0 gives you xi equal to 0 and b equal to infinity gives you xi equal to infinity, and hence I becomes integral 0 to infinity b to the power alpha minus 1. So v to the power alpha minus 1 makes it t minus u by t raised to the power alpha minus 1 xi to the power alpha minus 1 b is equal to t minus u by t into xi. Then dv is equal to t minus u by t d xi. d xi divided by bt is equal to t minus u into xi minus u minus t, that can be written as plus t minus u. So this is equal to we can write it as now. Okay, so this is integral 0 to infinity. 1 t minus u here will cancel 1 t minus u here. So t minus u to the power alpha minus 1 divided by t to the power alpha and d xi to the power alpha minus 1 into d xi divided by xi plus 1 we get. So this is this can also be written as 1 by t minus u upon t raised to the power alpha minus 1 integral 0 to infinity xi to the power alpha minus 1 d xi upon xi plus 1. So we get this I, the expression for I, which is minus integral 0 to u minus s by s to the power alpha ds over u minus s into s minus t, can be written as this integral 0 less than t less than u, and can be written like this when u is less than t. Now these integrals can be further simplified, and we can get the value of the integrals, and we get that for the case 0 less than t less than u, the value of this value of this integral I is minus u minus t raised to the power alpha minus 1 t to the power alpha pi cot alpha pi, and t minus u to the power alpha minus 1 over t to the power alpha pi sin alpha pi when u is less than t. Now let us first find the value of the integral 0 to xi to the power alpha minus 1 d xi over xi plus 1, and show that this is equal to pi over sin alpha pi. So integral 0 to xi let us show that this is equal to pi over sin alpha pi. 0 to infinity, it is 0 to infinity. Okay, so what we do here is that we will convert it into beta function. So let us put xi equal to t upon 1 minus t. When you put xi equal to t upon 1 minus t, xi equal to 0 gives t equal to 0, and xi equal to infinity gives t equal to 1. Okay, so let us call let us write integral 0 to infinity, then integral 0 to infinity xi to the power alpha minus 1. So t upon 1 minus t raised to the power alpha minus 1 we have, and this gives you d xi equal to, we can write it as xi equal to t minus 1 plus 1 divided by 1 minus t, which is minus 1 plus 1 upon 1 minus t. So d xi will be equal to minus 1 upon 1 minus t whole square into minus dt. So this is dt upon 1 minus t whole square. So we can put the value here. So t upon 1 minus t raised to the power alpha minus 1 for xi to the power alpha minus 1. For dxi we write dt upon t minus 1 minus t whole square, and 1 over xi plus 1. So 1 over xi plus 1 will be 1 over t upon 1 minus t plus 1. And what we get is, this is integral 0 to infinity t to the power alpha minus 1 upon 1 minus t raised to the power alpha minus 1 plus 2. So alpha plus 1, and here we get t plus 1 minus t, which is equal to 1. So this is 1 minus t here. So this is 0 to 1, and here also it is 0 to 1, because the limits of integration for t are 0 to 1. So this is equal to integral 0 to 1 t raised to the power alpha minus 1 minus t raised to the power minus alpha dt. We can also write that as in the form of beta function, t to the power alpha minus 1 minus t raised to the power 1 minus alpha minus 1 dt. So which is equal to beta function alpha beta mn, that is beta alpha 1 minus alpha. Now let us express it in terms of gamma function. So gamma alpha, gamma 1 minus alpha divided by gamma alpha plus 1 minus alpha, which is equal to gamma alpha, gamma 1 minus alpha divided by gamma 1. Now by the properties of gamma function, gamma 1 is equal to 1. So we get gamma alpha, gamma 1 minus alpha, since gamma 1 is equal to 1. Now it is well known that gamma alpha, gamma 1 minus alpha is equal to pi over sin alpha pi when for 0 less than alpha less than 1. So integral 0 to infinity xi to the power alpha minus 1 d xi upon xi plus 1 is pi over sin alpha pi. Similarly, we can find the integral 0 to infinity xi to power alpha minus 1 d xi upon xi minus 1, and can get pi cot alpha pi. Now when we take the special case alpha equal to half here, so when we take alpha equal to half, what we will get? So in the special case, alpha equal to half minus integral 0 to u minus s by s to the power half ds upon u minus s into s minus t. This is equal to minus u minus t raised to the power minus half upon t to the power half, pi cot pi by 2 in case 0 less than t less than u, and this is t minus u to the power minus half divided by t to the power half pi over sin pi by 2 when t is greater than u or u is less than t. Now this can be expressed in an alternate way like this. We can also write it as r minus integral 0 to u minus s to the power half will cancel with this one, and will get ds upon square root s into u minus s into s minus t equal to, now cot pi by 2 is cos pi by 2 over sin pi by 2. So, cos pi by 2 is 0. So, this is 0. So, 0 when 0 is less than t less than u, and pi sin pi over sin pi by 2. This is pi because sin pi by 2 is 1. So, t minus u. So, this can be written as 1 over t times t minus u into pi. So, pi over square root t into t minus u when u is less than t. So, this is the particular case when alpha is equal to half. Our identity reduces to this value. So, we will make use of this identity when we discuss the solution of Cauchy integral equation on a real line. Now, another identity let us discuss. So, we are going to integrate du upon square root u minus s u minus t over the interval maximum of st to 1, and we will show that it is equal to ln mod of square root 1 minus s plus square root 1 minus t over square root 1 minus s minus square root 1 minus t. So, integral du upon square root u minus s into u minus t. We want to prove that it is ln mod of square root 1 minus s plus square root 1 minus t divided by square root 1 minus s minus square root 1 minus t. So, there are two cases. One case is when s is less than t, and the other case is when s is greater than t. So, let us first prove for s less than t. So, let us assume that s is less than t. So, then the left hand side is equal to integral over t to 1 du over square root u minus s into u minus t, which we can also write as integral t to 1 du divided by square root u square minus s plus t into u plus st. Now, this integral is of the form, this integral is of the form integral 1 over square root ax square plus bx plus c. Dx upon square root ax square plus bx plus c, and we have the formula for the integral of 1 over square root ax square plus bx plus c, which is given by 1 by root a ln of square root ax square plus bx plus c plus square root a into x plus b upon 2 square root a. Here we have left an arbitrary constant term here, because that will not be used when you put the limits of integration, because it is a finite integral. So, in the case of a finite integral, the constant term that comes here we can ignore. So, let us see how we get this integral. So, this is equal to, we can write it as dx upon square root root a into x plus b by 2 root a whole square, and then we have c minus b square by 4a. When you square this, you get ax square, then you get twice root a into x plus b upon 2 root a, so we will get bx, and then we have square of this, which is b square by 4a. B square by 4a we have subtracted here, so we can write ax square plus bx plus c like this. And let us now put square root a into x plus b upon 2 square root a equal to t, which will imply that root a dx equal to dt. So we will have here integral dt upon t square plus alpha square, where alpha is equal to 4ac minus b square divided by 4a. Alpha square is this. So now we have to integrate this is raised to the power half. So we have to integrate 1 over square root t square plus alpha square. As what we can do is, let us put t equal to alpha tan theta. So this will become alpha sec square theta d theta divided by dt equal to alpha sec square theta d theta, and the denominator it will become alpha square sec square theta square root, so alpha sec theta. So this will cancel with this, 1 sec theta will cancel, and integral of sec theta d theta we know, integral of sec theta d theta is ln sec theta plus tan theta. We are not writing constant of integration because we are going to evaluate this definite integral. In the definite integral the constant is not required. So we have this ln. Now sec theta is what? Sec theta is equal to square root 1 plus tan square theta, and tan theta is t by alpha. So this is 1 plus t square by alpha square. So this is under root t square plus alpha square divided by alpha. So this is under root t square plus alpha square divided by alpha, and tan theta is also equal to t by alpha. So this is equal to ln under root t square plus alpha square plus t minus ln alpha. Let us substitute the value of t here. When we substitute the value of t, what we will get? So t square plus alpha square. T square plus alpha square is nothing but ax square plus bx plus c. So this is ax square plus bx plus c plus t. T is equal to root a into x plus b over 2 root a. This is expression for ln under root t square plus a square plus t minus ln alpha. Alpha is square root of 4ac minus b square upon 4a raised to the power half. Now we need to use this integral. We need to use this integral here to compute this definite integral. So we are not considering this constant term. We are simply taking okay, 1 over root a is also there. This root a we have missed here. So 1 over root a here, that we have missed all along. So 1 over root a, ln under root ax square plus bx plus c plus root ax 1 over b over 2 root a. We are simply considering this part. 1 over root a will be multiplied here also. So we are not considering this part, which is a constant, because it will get cancelled when we calculate this definite integral. Now we use this standard formula to evaluate this definite integral, and then the integral t to 1 du upon square root u minus s square root u minus t will be equal to ln under root u square minus s plus t into u plus st plus u minus s plus t by 2. Now let us put the limits. Upper limit is 1, lower limit is t. Then we shall be getting this ln under root 1 minus s into 1 minus t plus 1 minus t plus t minus s by 2 minus ln t minus s by 2, and which we can easily show because ln under root this is nothing but, let us see how we get this. This expression, this one is nothing but ln under root 1 minus s into 1 minus t plus 1 minus t, which can be written as 1 minus t whole square under root 1 minus t whole square plus t minus s by 2. So t minus s by 2 we can write as under root 1 minus t whole square minus under root 1 minus s whole square divided by 2. This will be giving 1 minus t minus 1 minus t minus 1 minus s. So this is s minus t, so I can write like this, so that it is t minus s. So t minus s can be written like this, this divided by t minus s by 2. So t minus s by 2 again can be written as like this, under root 1 minus s whole square we can write like this. So ln of this quantity, and this is equal to ln of here we can write it as 2 times square root 1 minus s into 1 minus t, and this is under root 1 minus t whole square. From this we are subtracting under root 1 minus t whole square by 2, so we will get plus sign. So we will have under root 1 minus t whole square plus under root 1 minus s whole square, and then in the denominator we will have under root 1 minus s whole square minus under root 1 minus t whole square, and this, now this is what ln under root 1 minus t plus under root 1 minus s minus under root 1 minus t plus whole square. The numerator can be written like this, and we have under root 1 minus s minus let us factor in the denominator. So this cancels with the numerator, this one, and we get ln under root 1 minus s plus 1 minus t here under root ln under root 1 minus s plus under root 1 minus t upon under root 1 minus s minus under root 1 minus t. Now which proves this the result, the identity for s less than t. Similarly, when we take s greater than t, we can show that it is integral maximum of s and t will be then s. So integral s to 1 du upon under root u minus s under root u minus t is equal to ln under root 1 minus t plus under root 1 minus s over under root 1 minus t minus under root 1 minus s. Now so we can combine this equality and this equality and write integral over maximum s t to 1 du over under root u minus s u minus t to be ln of under root 1 minus s plus under root 1 minus t upon under root 1 minus s minus under root 1 minus t, because when s is less than t, then under root 1 minus s will be more than under root 1 minus t. So, this modulus will disappear, and when s is greater than t, then under root 1 minus s will be less than under root 1 minus t. So, this will be changed to under root 1 minus t minus under root 1 minus s, and we will get this. So, this proves the second identity. So, with this I would like to conclude my lecture. Thank you very much for your attention.